Okay, so we give the general data of the sun. And then from there we go to the interior, and then we go into the surface features and stuff like that. We see the sun's mass is very, very huge, 1.99 times 10 to the 30 kilogram, 333,000 times the mass of the Earth. The radius of the sun, 696,000 kilometers, which is 109 times the size of the Earth. That means you can fit 109 Earths across the diameter of the sun, 109 Earths, one after another. Density, 1.41 grams per cubic centimeter. Remember, density means how much mass it has divided by its volume. So even though the sun is very heavy, its volume is very big. So when you divide them, you don't get a very big density. If the density of water is 1 gram per cubic centimeter, density of the Earth 5.5, Moon 3.3, the sun is the least out of all those. The sun's density pretty much resembles Jupiter's density, okay? Something like that. So Jupiter is like a mini sun. Luminosity of the sun. This is something that we haven't talked about a lot when it comes to planets, because planets don't have luminosity. They don't give their own energy. Stars have something known as luminosity. It's how much energy they give off, okay? So 3.90 times 10 to the 26 watts. This is the same watts that you use when you say, I want to go buy a 100-watt light bulb. It's how much power the sun is giving you. Then imagine how many light bulbs this would be equal to. 3.9 with 26 zeros followed after that, okay? Solar constant, 1,370 watts per meter squared. What that means is how much of the sun's energy comes and hits the Earth's surface per meter squared, okay? 1,340 watts per meter squared, that's quite a bit. If you think of it, imagine you have a house. Of course, this solar constant depends also on where you live, the city that you live. Is it more sunny or is it more cloudy? But it's on the average, you know. So imagine you had a house with a roof, and let's say the roof, just to make simple, let's say the roof total surface area was 100 meters squared, just for the sake of argument. How much power would be hitting that roof? How much solar power? If the solar constant is 1,370 watts per meter squared, 100 meters squared, and then you would be 1,37000, 137 watts. Okay? So that means sometimes we use the term kilowatts. That would mean 137 kilowatts of solar energy is hitting the home every day. So then you use this to put solar cells there, okay, solar panels, and then the solar panel, the goal of it is to trap this energy and then to to use it later on, maybe at night and stuff like that. So the solar cells are not 100% efficient. They're not going to be able to take all of this energy and convert it to electrical energy. They're probably going to be maybe 10% efficient or something like that. So let's say, for the sake of argument, they are 10% efficient. 10% efficient. What does that mean? That means out of all this energy hitting the roof, only 10% of it is going to be converted into electrical energy that you can use in the house. Okay, even then, that's still not bad. If 10% of this is used, how much would that give you? So basically, it's like taking this number, multiplying it by 0.1. 137,000 multiplied by 0.1, what do you get? 13700 watts. That's still 13.7 kilowatts in the language of kilo, you see. So what I did is reduce one of the zeros, and then you go 1, 2, 3, 13.7 kilowatts. So you're still getting 13.7 kilowatts of electrical power from the sun that you're able to use as electricity. So in the future, this is going to be very, very common. Even now, you can apply to get a solar panel in your house, and the government will subsidize some of your money that you put in. So it's a wave of the future. It's not going to necessarily replace everything else, but it's going to come along to help. Maybe even we're going to have cars with solar power. Maybe the windows of the car can have little solar cells in them, and then they can help power the battery of the car. And so in the future, we're probably going to be using wind power, solar power, everything in conjunction, you know, together to help out. So that's basically what this means, solar constant. Okay, surface temperature of the sun. 5,800 Kelvin. That means this is how hot it is at the surface. That's very, very hot, 5,800 Kelvin. Venus, which was very, very hot planet, is the hottest planet, maybe is 800 Kelvin. Maybe at best 1,000 Kelvin. It doesn't even come close to the sun. The core temperature of the sun, 15.5 million Kelvin. So as you go inward, the sun is going to get hotter, hotter, hotter. By the time you get to the core, it's in the millions and millions of Kelvin. Rotational period of the sun at the equator, 24 days, 16 hours. So the sun rotates once around its axis every 24 days, which means almost a month, roughly. It takes about a month for the sun to go around. And the way that we know this, the best way to figure this out is by tracking solar spots, sunspots on the sun. You see here? This would be November 9th is here. So some solar spots are starting their rotation on this side. And by November 12th, they're here. By November 14 here. November 15 here. 17, 19, they are here. So roughly that's from 9 to 19, that's 10 days. In 10 days, they've gone from the left side to almost the other side. You see, not quite, but almost the other side. Maybe by 11, 12 days, they would have come all the way here. Okay, so it would take them about 12 days to make half a rotation around the sun. So a complete rotation would take how many days? 12 times 2, 24 days. You see? So if we just spot them and we go around, then we should be 24 days to come back to the same point. Surface gravity. We've seen that before when we talked about planets. If you ever were able to stand on the surface of the sun, of course you're going to melt, but if you were to stand, you would weigh 28 times what you weigh here on Earth. So the gravity is enormous. Inclination of the axis, 7 degrees. So just like Earth's axis is inclined by 23.5 degrees, right? That's 23.5 degrees, and that's what causes our seasons. The sun's axis is also tilted by about 7 degrees. And how do we know that? Also by studying the pattern of sunspot rotations. We can determine the inclination of the axis. Angular diameter of the sun, what that means is how big does the sun appear to us from Earth? And that means about 32 arc minutes. Remember, 60 arc minutes was 1 degree. So 32 arc minutes is about a half a degree. So what that means is about, maybe if you get a nickel or a penny or a dime, and you can put it at about an arm length, and that would be about the size of the sun. Okay, about a nickel is probably better. You can extend it out with the hand, and that would be the angular diameter. Remember, the angular diameter of the moon is also about half a degree, which is why the moon can give you a total solar eclipse. Even though the moon is smaller, but it's closer to us, right? So if the conditions are correct, the moon can completely cover the sun. Okay? Why? Because its angular diameter is also about 30 arc minutes or so. Okay. So I think that's it. So that's some of the general data.